Okay, thanks for the very nice introduction, and thanks for having me today. So today I would like to discuss dense retrieval. So I actually believe this morning Jason already talked a lot about retrieval augmented models in DialDoc. So today my perspective is slightly different. So I would like to mostly focus on phrase retrieval models. So before I start, I need to say that a majority of this work was actually done by Jinhui Li, who is currently a visiting postdoc in my research group. And he's also in the audience today. And this is also a joint work with Alex, who is a PhD student of mine at Princeton, and also Mingjun and Jiwon from Korean University. So dense retrieval has been very successful in the past 1 or 2 years, and has been shown very effective in open domain question answering and also many other knowledge-intensive NLP tasks. So unlike this kind of sparse text retrieval methods such as TF, IDF, or BM25, which basically represent text as a weighted factor words models, and then we can conduct search with an inverted index. And these dense retrieval methods basically aim to map all the text units into a low-dimensional continuous space. And we can directly do the efficient maximum product search efficiently in this space. So this figure is from the DenseSPI retrieval, or we call the DPR paper. So this is work I did with Scott Yi and a few other Facebook researchers over 1 year ago. I believe Scott is also at the workshop today. So basically we show that in this work, DPR can actually outperform BM25 by a large margin on a bunch of the question answering tasks. And this is even better than BM25 if we only have like 1,000 examples. So actually, I'm not going to talk about DPR today, but you will hear it many times in this talk. And as you can see from the table on the right here, is actually from the recent Q benchmark. So basically, this table shows that over a range of the NLP tasks, including question answering, fact checking, anti-linking, slot filling, and knowledge-grounded dialogue tasks, DPR can also greatly outperform the TF, ITF basically across the board. So for most of the existing work in the dense retrieval, most of the paper basically focus on the passage retrieval. And here the definition of the passage is actually a design choice of the system. For example, the DPR basically choose to use like a 100 text block as the retrieval unit. And there are also some recent work basically showing, for example, this very good like a Lang et al. Tackle paper, basically shows that if we keep increasing the passage length, and using the fixed length vectors actually are not expressive enough to encode all the information in the passages. So that would actually lead to a performance drop. So in this talk, I'm actually going to take the opposite extreme, and I'm going to talk about a paradigm called phrase retrieval, which can be actually sort of the most fine-grained retrieval unit. So here the definition of the phrases is actually very general. So they don't necessarily represent linguistic phrases. So here the definition of phrase is basically any contiguous segment text up to, let's say, 20 words. And here there's also a very important notation here is that here the phrases actually are contextual. So the phrases are not just means that the words that actually contained in this phrase. It also includes all the context that this phrase actually appears in. That means that if you can find the phrase, you can also know which sentence or passage or documents that this phrase comes from. So today I would like to actually discuss 2 research questions. So the first question is that, is it actually possible to learn the dense repetitions for the phrase retrieval at a very large scale? Let's say there's billions of the phrases, for example, for the Wikipedia scale. And the second question is, if we can learn the phrase retrieval at scale, can we just use the phrase retrieval as a very basic building block for like basically also of the retrieval problems that we care about, for example, the passage retrieval or document retrieval? So I believe the answer is yes to both questions, at least to a great extent. So the first question was actually already answered in one of our ACL papers this year called DensePhrases. And I believe that Jin actually also presented this paper yesterday at ACL. And the second question is actually new work that we recently did. And this is also my very first time talking about this line of research. So let me directly jump in and talk about how we can actually learn the dense repetitions of phrases at a billion scale. So first, let me make it very clear by defining what is a phrase retrieval. So here the goal is basically we take a piece of text And we take a phrase in the text. In this example, the police is actually a phrase in this piece of text. So here the police is the basic name of the band. And here the goal is to encode this phrase, again, together with the context as a vector. So if we consider a large corpus such as English Wikipedia, and all the phrases up to 20 words, so there will be roughly like 60 billion phrases that we actually need to encode and index them offline first. And then we have a question or any other input query that we are actually interested in. For example, the question here could be, who thinks don't stand so close to me? And we need to encode this question into a vector as well. And then we can just do the maximum inner product search in this dense space. And then we can retrieve the phrase with a maximum inner product score. So in this case, in the question answering context, basically we want to retrieve the police as the answer to this question. So this problem is actually a very difficult problem. So the main challenge actually comes from its scale. So compared to the dense passage retrieval, which considers 21 million passages in Wikipedia. So here the size of the phrases is actually like basically several orders of the magnitude larger compared to the passage retrieval. Because we also need to consider so many phrases at once. So it's also a much harder learning problem compared to the passage retrieval. So even if we can solve this like a learning problem, how to store all these dense vectors of the phrase repetitions can also pose a very big challenge. So you may wonder, given it's actually a very difficult problem to solve, why do we even want to solve this problem? So answer is really, if we can solve this problem, so phrase retrieval can give us actually extremely fast, like runtime efficiency. So if you are familiar with this family of the very popular retrieval rhythm models, if we want to do question answering or like similar related tasks, essentially we need to first retrieve 100 passages, and then we need to apply a second stage model on top of these passages to get the final answer. And these days, basically this second stage rhythm model is implemented either by a BERT or by a T5 model, which contains like hundreds of millions of parameters and could take a lot of time in the practice use. But if we can actually manage to do the first retrieval, that means that we can essentially just throw out this second stage. And we can directly just retrieve the final answer from like a very large collection of the phrases. And this can give us great efficiency at the inference time. So next, I need to say that this whole idea of the doing phrase retrieval is not from me, at least. It was actually first pioneered by Minjun Xiu and other researchers in their 2018 paper for a single passage reading comprehension setting. And then later on, they actually implemented this idea in this system called Dense-Sparse Phrase Index, DenseSPI work, in their ACL 2019 paper for open domain question answering. However, the way that they got this DenseSPI work at that time is basically for every single phrase, they need to build a dense repetition as well as a sparse repetition. So here, the dense repetitions are basically the vectors that learned from the BERT encoders. And the sparse repetitions are basically the traditional TF-IDF vectors for the corresponding document and the paragraph. So essentially, they need to concatenate both the sparse and the dense repetition to represent every single phrase. But you actually cannot really parallelize the sparse and dense search. So in practice, they actually do both the sparse and dense search separately. And they also developed several strategies to tackle this problem. So this work in 2019 has demonstrated great like runtime efficiency, but it also had a very clear drawback. So the first problem of this model is that it actually greatly underperformed the retrieval rhythm models that I just described. And another problem of this model is that this model actually also heavily depends on the sparse component. So basically in their evaluations, they show that if they just remove the sparse repetitions, the performance will drop a lot, at least on the spot data set. And also because they have to store both the sparse and dense repetitions for every single phrase. So they also require very large storage. So it took basically 1.2 terabytes to store the whole phrase index. So next, then I'm going to show you what we actually did in this project. So we call this project as dense phrases. So the first thing we did in this dense phrases project is that we actually completely removed all the sparse repetitions. So by removing the sparse repetitions, we actually were able to reduce the storage by 4 times. And the system is also much faster than the previous system. It also will achieve like 10 times latency improvement. And actually, a more important thing is that we also greatly improve the performance of this system. And it finally actually matched the retrieval rhythm model, such as DPR, in actually a bunch of the open domain question answering tasks. So here is actually a quick preview of the results. So as you can see from the last column here, this is basically the accuracy, the exact match accuracy on the natural questions data set. As you can see that this is basically the previous phrase retrieval models. Our performance is actually much better than the previous phrase retrieval models, and also can match the basic DPR performance on natural questions. Although the DPR model, this model actually was trained on even more data sets. But if you look at the speed, so our model was able to achieve 20 to 30 times faster on GPUs. And this model, because we don't need to run the BERT model, run BERT or T5. So we are able to run this model even on CPUs. And it can actually process more than 10 questions per second on CPUs. And if you look at the storage, so as I said, like compared to the previous phrase retrieval models, we are able to actually make it like 4 times smaller. And our recent work was, if I have time to talk about that, actually we are able to actually even further reduce the storage from 300 gigabytes to 80 gigabytes for the phrase repetitions. So this size is basically comparable to the DPR index, but still like is actually much faster, and also the accuracy are actually very competitive. Okay, so how did we do this? So there are several key ideas behind these dense phrases. So the first idea is that we actually need to learn the query agnostic phrase repetitions from the question answering supervision. And after we learn these phrase repetitions, we also need to learn how to scale up these phrase repetitions to a very large collection of documents. By doing this, we actually need to consider incorporating many different types of different types of negatives. And finally, we also propose a strategy called query side fine-tuning. So we found that this strategy can actually improve both the in-domain and also can support transfer learning in this paradigm. So next, let me just go through all these ideas in detail. So let me start from the basic architecture of the dense phrases. So as you can see from this figure, so in the dense phrases, our goal is basically to learn a phrase encoder and also learn a question encoder. So we first basically take a piece of text and pass this into a phrase encoder. And then we can get a sequence of contextualized vectors. And then we can represent the phrase vector as a concatenation of start and end vectors. And this design is actually very crucial because we can represent the phrase vectors as start and end vectors. That means that at inference time, we only need to store the contextualized word vectors instead of the phrase vectors. So this can make the size at least 20 times smaller. So basically, this is basically the basic design of the phrase vectors. And similarly, we also represent the question vector as 2 parts, so denoted by Q star and Q end here. So essentially, we just pass the question to the 2 separate question encoders, get 2 vectors, and then concatenate them. So by decomposing the question phrase repetition into 2 parts, so we can just compute the inner product between the question and the phrase as a sum of the Q star and H star and the Q end and H end. And at the inference time, so we basically just need to encode all the contextualized word vectors. Then we can just search the start and the end vectors separately, and then we can just combine the start and end points, and then finally return the phrase. So in this work, we actually use the span BERT instead of the BERT as an encoder, because span BERT is actually believed to compress the information of the span into its 2 endpoints. And this is exactly what we need for these phrase repetitions. And both encoders will be actually fine-tuned using the question answering supervision that I'm going to talk about in the next slide. Okay, so the first step here is we want to learn the 2 encoders, question encoder and phrase encoder, from the question answering supervision. So the task here is, given a passage and a question, we want to predict which span or which phrase is actually the correct answer. So this is exactly the setup of the reading comprehension. So we can basically easily use the natural questions or SWOT to train these models. But the difference here is that we actually need to use a formulation we just defined to solve this problem. So in this case, basically the question and the phrase repetitions are actually fully decomposable. So they're actually these are very different compared to the cross attention models. So there are several key challenges that we actually need to solve here. And I don't want to spend too much time here, so I actually encourage you to check out the paper for more details. So the first challenge we want to solve here is we found that the question answering supervision is actually too sparse. So basically that means that there is only one or very few questions posted on each passage. So to solve this problem, so basically our solution is very simple. We try to generate more questions for every plausible phrase in each passage. For example, in this example, like this phrase is basically the name of this album. So we are trying to generate a question such as what is the third album of the Police, which can be actually the question. The answer can this phrase is basically the answer to this question. And the second challenge we are trying to solve here, and is also a known problem, is that this dual encoder model always actually underperforms the cross attention model, which is basically the standard reading comprehension model. So to solve this problem, so we basically try to propose to use a knowledge distillation to learn from the cross attention models. So basically by performing these two steps, the question generation and knowledge distillation, we can actually greatly reduce the gap between this model and the standard cross attention reading comprehension model. So that's basically the first component of the whole model to learn this kind of query agnostic phrase repetitions. Okay, so after we learn the question, the phrase encoder from the reading comprehension model data sets. So the next problem is that we actually need to consider how to scale up this model to a large collection of passages. So here the task is given a collection of passages, how to predict which answer or which step is actually the correct answer. So the solution here is trying to incorporate a lot of the negatives in a contrasted learning framework from the basically from the a lot of negative from the larger collection of the documents. So in this work, we consider two types of negatives. And the first type is called in-batch negatives. So the in-batch negatives, the idea is basically to use other gold phrases in the same mini batch as a negatives. So basically like all these kind of other gold phrases in the same mini batch. And in-batch negative is basically a very clever and cheap way to obtain a lot of negatives. And this has also been shown effective in the previous dense-sparse retrieval work. And in this work, we also introduced a new idea we call the pre-batch negatives. So here the idea is that because we believe that learning phrase repetitions is actually much harder learning problem, so we actually need to incorporate more negatives. So by doing this, we basically build a first in, first out queue. And we try to cache the recent previous seed mini batches with a gradient detached. That means that we are not going to backwardate to the previous phrase repetitions. So by doing this, we can actually obtain like B the batch size, C basically the number of previous mini batches as additional negative examples. So this is basically just one way to actually incorporate more negatives in this training paradigm. So you can see from this table, we basically find that by using both the in-batch negatives and the pre-batch negatives can actually improve the performance significantly. And we also find that we cannot keep increasing the number of the previous mini batches just because of repetitions in the previous mini batches can get outdated very quickly. So basically we just use C as 2 as a final solution. So up to this point, so we are basically able to build learn the phrase repetitions. So and then after this step, we are just going to actually encode and index all the phrase repetitions. And this would actually take 20 hours on like 424 gigabytes GPUs. So this actually a pretty, it's manageable, but it's actually a very expensive operation. So we only want to build a phrase index only by once. So the next question is how are we going to use this phrase index for question answering and other knowledge intensive NLP tasks? So we also propose, this is basically the last step of this work, that we basically propose a solution that we basically fix the phrase index. And we propose to only fine-tune the query encoder to perform various different tasks. So here the idea is that we use the phrase index to return the top K phrases. And we basically just try to maximize the marginal log likelihood of all the phrases that are top phrases that actually can equal to the correct answer string. And we found there are two advantages for doing this. So the first is that actually can reduce the discrepancy between this like training and also the testing phase. And the second advantage is that if for some data sets that we have never used to build a phrase index, we can only train the query encoder for like a new task, for unseen new task. So this can actually effectively support transfer learning for some other unseen tasks. So as you can see from this table, so basically here we try to use only the natural questions to build a phrase index. And here, this column is the basic evaluation of natural questions. We find that if we just do the query side fine-tuning on the natural questions, we can still further improve the performance greatly from 30 to 40.9 accuracy. And for some other query tasks, basically the improvements are even larger, such as web questions or track, because we never use the web questions or track to build a phrase index. Okay, I think I'm actually behind time. So this is basically the sketch of the approach that we actually build our DensePhrases. So let me just show you a bit more results. So here is a comprehensive set of evaluation for the 5 open domain question answering tasks. And again, the phrase index is only built using squad and natural questions. And basically for the other question answering data set, we just use them for the query side fine tuning. And we basically found that compared to the dense-sparse retrieval, the performance are actually very competitive and basically similar or even better in some cases. So we also try to use DensePhrases for some other non-QA tasks. So here we try to do this for the slot filling. So here the task basically we take a subject and a relation, and our goal is to predict the object. So here the query is even not a natural language question. So we just concatenate the subject and the relation and put the ACEP token in the middle. So this is just like a fake or pseudo query that the model has never been seen. So we just try to reuse this like a phrase index using the natural questions in the slot. And then we only fine-tune the query encoder on this slot filling task using like 10,000 triples. We actually can achieve very, very good performance, or basically like much better than DPR and RAG across the board. And we also build a demo for these DensePhrases. So if you're interested, you can go to this URL and you can play with our DensePhrases demo. Let me just play this very quick. Actually, I should say, actually, Jim built the whole demo by himself. Yeah. So basically, as you can see from this like animation, so you can also play with our demo. So this system can be actually very, very fast, and also can return the basically phrases for different types of input queries in a bit of real time. Again, like you can process like more than 10 questions per second. So it's actually very fast and also very accurate. Okay, so I think I only have a few minutes left. So I'm just going to be very quick to talk about the second part, So we are pretty happy with what DensePhrases can do at this point, at least for the question answering and the slot filling. But we want to think about this further. So the question we want to ask is, if we can do the phrase retrieval very accurately, can we just use the phrase retrieval as a basic building block for basically almost all types of retrieval problems? So if we can do that, what should be the advantage for that? So here the motivation is not really all the LP tasks actually require phrase retrieval, right? Even for the question answering task, like if you want to ask a why question, such as why is the sky blue? So you don't want the system to just return a single phrase. You might want the system to give you a sentence or even several sentences that is actually form a complete answer to this question. And for some other tasks like knowledge-grounded dialogue, you don't a phrase will be just not enough. So you actually want to retrieve the piece of text that is actually relevant to the utterance in the dialogue. And then we want to build a system to generate text based on this kind of a piece of text instead of just a single phrase. So here we actually build on a very simple intuition here is because the phrase is actually the most fine-grained unit. So if we can retrieve the phrases, that means that this system can actually naturally entail retrieving the passages or even documents. So basically phrase retrieval, if you can do the phrase retrieval, you can also do the passage retrieval. But the opposite direction is actually not correct. So if you can do the passage retrieval, that doesn't mean that you can do the phrase retrieval by this direction or it's hold. So here the basic question we want to ask is, can we directly use the DensePhrases for the passage or document retrieval task? If we can do that, what's the connection between the phrase retrieval and the passage retrieval? So here is a bit of comparison between the dense passage retrieval and dense phrases. So for the dense passage retrieval, basically we just want to encode basically the whole passage using one single vector. We just take the vector from this CLS token. But for the dense phrases, basically we can view the passage repetitions as a set of the phrase repetitions. So if we want to get the passage repetition, so basically the very straightforward way to think about the passage score can be defined as basically the maximum of the phrase scores that actually appear in this passage. So to test this idea, we just did like apples to apples comparison, comparing the dense passage retrieval and the dense phrases. So here we don't retrain the dense phrases, we just use it as an out-of-the-box solution. And we also follow the DPR evaluation and use the 100-word block as a passage. So as you can see from this figure, so here is basically the passage retrieval accuracy on the natural questions and the trivial QA. So we actually found that this is actually very surprising to us. So basically, because we don't train the dense phrases for full passage retrieval task, but we still found that by just using the dense phrases out of the box, dense phrases already outperforms the DPR dense passage retrieval. And this improvement is especially large for the smaller number, for the top ranked results, such as top 1 or top 5 results. So if we compare, let's just say top 1 results compared to the dense passage retrieval and dense phrases. So we basically find that the basic improvement are very large, especially for the trivial QA is basically like 17% improvement. So we also want to understand what's going on here. So we try to compare the dense passage retrieval and the dense phrases in terms of their training paradigm. So we basically find that dense passage retrieval learns from the passage supervision, but dense phrases learns from this answer or the phrase as a supervision. And they as a positive examples. And they both use in-batch negatives. But the dense passage retrieval also uses additional BM25 to mine some hard negatives. But dense phrases has never used any other explicit hard negatives. So we can also argue that this is actually one advantage of the dense phrases. So basically, so we actually hypothesize that for the dense phrases, because it actually need to predict the phrases of the passage, so we can basically just review the other phrases in the same passage as a hard negatives. So that's why the learning the phrase repetitions can also do the passage retrieval very well. Okay, I want to very quickly describe this. So by observing these results, basically we find that okay, we can just take the dense phrases to return return some passages, and we can still train like a reader or generator on top of the passages that return from the dense phrases. So we actually consider this fusion in decoder model. I think Jason also talked about this morning. So this model is actually training a T5 model on top of the top 100 passages returned from the DPR. And this model is actually very, very expensive. They actually require using like 64 V132 gigabytes GPUs. So it's actually a very expensive model. So basically we show that if we use a sense decoder, we can just use a much smaller number of the passages from dense phrases, and then we can still get very competitive performance compared to the fusion encoder. And again, like I think this GPU configuration is basically beyond the reach of most of the academic labs. So we basically can just train our this like a T5 model on a much smaller number of the phrases, number of the passages, and we can still get a very good performance. And I want to, finally, we also have one more like a key insights that we actually derived from this observation. So if we know that these phrases can be thought of as a set of the phrase repetitions in a passive repetition, and if we want to just use the dense phrases for the passive retrieval, so we are actually able to make the dense phrases index size much smaller by just controlling the number of the phrases per passage. So we actually tried a lot of experiments by just trying to filter out some phrases in the in the passage. And as you can see from these results, basically we are able to only return, let's say, 8.8 phrases per passage. And we also try to use a product quantization to make the index size smaller. And finally, we are able to actually achieve basically only a phrase index of 30 gigabytes. And this is basically the half size compared to the DPR. And still, if we only care about the passage retrieval accuracy, the accuracy is actually very similar, competitive, or even better than the DPR accuracy. Okay, I'm going to skip this slide, but basically the idea is that we also try to use dense phrases for the document retrieval task. And we also evaluate this on the anti-linking and the dialogue task. And we found that basically dense phrases can be also very competitive for the document retrieval, but we also need to do some query-side fine-tuning on the document supervision. All right, so let me just wrap up here. So basically in this talk, we show that dense phrases is basically we are able to do the billion level phrase retrieval. And it can actually perform, it can be actually very accurate and efficient for question answering and the slot filling task. And what I really want to emphasize in this, the very last bit of this talk is, if we can do the phrase retrieval, which is the most fine-grained retrieval unit, it can also naturally entail the passage and also the document retrieval task. And also phrase retrieval models actually can be also made much smaller and also more efficient. So this is I have a very high hope for this basic line of direct research. So actually, I really think that we can just rethink the phrase retrieval as basically a practical and also versatile solution, basically for all these kind of different levels of multi-granularity retrieval task. Okay, so I'll just end here, and our code and the model and the demo can be found on this URL. And yesterday I just checked what I should end, what I should say when I end this presentation. So if you ask those phrases what to say after presentation, maybe I should say have a nice day. Yeah, that's all. Thanks.